Now, the question we want to start with in this class is, how do I find the derivative of y equals the sine of 3x? Well, in the last section we learned that the derivative of sine x is cosine x. But here we have sine of 3x. So the first thing we want to identify is that y is actually the composition of two functions. So in terms of this, if we said, well, f of x is going to be sine x, and g of x is equal to 3x, we would have y is equal to f circle g of x. And remember, function composition says we put the second function into the first function. So everywhere in f where I see an x, I'm going to replace it with g of x. And that would indeed give me the sine of 3x. So y is the composition of the sine function and the function 3x. Oftentimes, we are going to want to write this composition but use a different intermediate variable. So this could be realized in a different way. And what I mean by that is for f, we could write f of u equals sine u. And then we could make our inner function u equal to 3x. So then notice y would still be equal to f circle u of x, right? It's just a different way to write these things out. It turns out that writing things like this will be helpful in what we're going to do next. So it's probably been a while since we've done function decomposition, which is the idea of recognizing a function as the composition of some other functions. So let's go ahead and identify our inner and our outer functions. So in this example, we have the sine of x squared. We would identify f of u as being the sine of u, and our inner function, u, would be x squared. And in this example, we see that the u is the function that is inside of the sine. So our sine is our outer function, and the u is our inner function. And as mentioned, this is equivalent to f of x equals sine x, and g of x equals x squared. All right, now let's look at b. So a was the sine of x squared. What is our b going to be? Well, what's our outer function this time? Well, our outer function, the sine, is inside of the squaring function. So f of u is going to be u squared, and u is going to be sine x. Or in the other notation, f of x equals x squared, and g of x is equal to sine x. So notice, sine x squared is not the same as sine squared of x, and the composition, although they use the same functions, inner and outer matter. So in case you didn't remember, function composition is not a commutative operation. So the order we do it in matters. So f circle g will not, in general, equal g circle f. So in this time, our outer function was the squaring function, and our inner function was sine. All right, for our next one, we have x squared plus 1 inside the square root, so it's the radicand. So f of u is the square root of u, and u is the inside function x squared plus 1, or f of x equals the square root of x, and g of x is equal to x squared plus 1. All right, so the tangent is inside the exponential function e. So f of u is going to be e to the u, and our u, as our inner function, is going to be tan theta. Written in our other notation, f of theta would be e to the theta, and g of theta would be tan theta. All right. So now we are ready for our theorem for this section. And the theorem is called the chain rule. The chain rule states if g is a differentiable function at x and f is a differentiable function at g of x, then the composite function y equals f evaluated at g of x, or f circle g of x, is differentiable at x, and y prime is equal to f prime evaluated at g of x times g prime of x. So it's the derivative of the outside evaluated at the inside times the derivative of the inside. That's the prime notation. The derivative of the outside, so f prime, composed with or evaluated at the inside, g of x, times the derivative of the inside. In Leibniz notation, we're going to have that dy dx is equal to dy du times du dx. For chain rule, Leibniz notation shines. You can use either one, but you will discover, especially when our chains get more complicated, that the Leibniz notation is like a roadmap. It's going to tell us how to get from A to B. It has a lot more notation involved, but that notation is helpful. So one thing you'll notice is that our differentials are going to behave a lot like fractions. So in this sense, we have dy dx is the goal we're trying to find. We're going to differentiate through the intermediate variable du. Well, if I had a fraction dy over du and the fraction du over dx, those guys would reduce out, and then what would be left behind? Oh, dy dx, which is what I was trying to find. So this roadmap will help us determine what the intermediate variables are and what we need to differentiate through in order to get our final answer. I will show them both ways, but I have a very strong affinity for Leibniz notation. And for those of you that have to go on and take Math 241, i.e. Calc 3, you are going to have to use Leibniz notation, because when you have more than one variable, instead of creating a straight line chain like what we're going to have in this class, you're going to get multi-branching chains. And if you try to do it with the other notation, it's not possible. So this notation generalizes, whereas the prime notation doesn't. So it kind of gets stuck as we move on. All right. Pros and cons of each approach. So let's go ahead and take a look at example 2. So first thing to note, all of the examples for example 2 are the same things we did in example 1. So we already know what f and g are, right? So from example 1, in this case, we know f of u is equal to the sine of u, and we know u is equal to x squared. So y prime is equal to df du times du dx. I've just written down the chain rule. But now I have f of u up here, so what's the derivative of f with respect to u? So what's the derivative of sine u? Well, the derivative of sine is cosine. So we get cosine u times, now we're done with f, we look at u. What's the derivative of u with respect to x? So du dx, well, the derivative of x squared is going to be 2x. So we get 2x cosine u, but we know what u is. U is x squared. So we get 2x cosine x squared. So the derivative of the function composition of sine and x squared, so the derivative of sine x squared is 2x times the cosine of x squared. So, using the other notation, if we have f of x equals sine x, and we have g of x equals x squared, our other notation says y prime is equal to the derivative of the outside evaluated at the inside times the derivative of the inside. So f prime, the derivative of sine, is still cosine. And the derivative of g is going to be 2x. So we get f prime evaluated at g. So it's going to be cosine evaluated at g times g prime, which is exactly the same thing. 2x cosine x squared. So notice, it's the derivative of the outside, that's this, evaluated at the inside, that's this, times the derivative of the inside, right? Two different ways to do the same thing. Personally, as I said, I think the Leibniz notation is simpler and cleaner, but if you like the other method, there is nothing wrong with it, and sometimes I do use it. So we should know both, but whichever one makes you the happiest is probably a good method. But as we'll see, as these chains get longer, the method I did second gets more and more difficult. All right, so we had f equals u squared, and u equals sine x. So then y prime is going to be df du times du dx. So the derivative of f, so the derivative of u squared is 2u times the derivative of u with respect to x, the derivative of sine is cosine. We then substitute our u back out, so we get 2u, but u is sine, so sine x, cosine x. So the derivative of sine squared is 2 sine x cosine x. All right, let's take a look at C. So our decomposition this time is f is the square root of u, and u is x squared plus 1. So y prime is still df du times du dx. And the square root of u, remember, is u to the 1/2 power. So our derivative is going to be 1/2 u to the negative 1/2 times du dx, which is 2x. 2's reduce out, and that gives us x over, moving it into the denominator makes it a positive 1/2 in the square root of u. But what's u? X squared plus 1. So we get x over x squared plus 1 and a square root. So the derivative of the square root of x squared plus 1 is x over the square root of x plus 1. All right, our last example, at least of this type, so we're going to have f is e to the u, and u is equal to the tangent of theta. So y prime is df du times du dx. So the derivative of e to the u is just e to the u times the derivative of tangent. Sorry, I wrote dx, but it's a function of theta. So this is d theta. The derivative of tangent theta is secant squared theta. Then we substitute out our u. So we have secant squared theta times e to the tangent theta. So our derivative of e raised to the tangent theta is secant squared theta times e raised to the tangent theta. All right. Well, we're going to jump over this next page for a second to example number 3. And we want to keep finding some derivatives. All right, so we look at what we have going on here. I have x minus 2 cubed times x cubed plus x minus 1 to the 6th. So the first thing I'm going to notice is that I have a product rule, right? Because I have two things that are multiplied together, but then those things that are being multiplied together have function composition in them. So this is going to be a product plus chain rule. So let's start with our product rule. So in our product rule, I'm going to start with each of them. So my f is x minus 2 cubed, and my g is x cubed plus x minus 1 to the 6th. And now I need to find f prime. But what I'm going to notice is that this is function composition. So I'm going to have to push in a level. So we have to use the chain rule. So inside my chain rule, I now have f is equal to my cubing function, and u is equal to x minus 2. So then my derivative, f prime, is going to be df du times du dx. So df du, the derivative of u cubed is 3u squared, and du dx is going to be 1. So then finally, back substituting all of that out, I get 3 u squared, u is x minus 2 squared, times 1. So my derivative of x minus 2 cubed is 3 times x minus 2 squared. Okay, so now I found f prime, but I have the same thing that happens over here. I have composition again. So I've got to use the chain rule again. So this time I have g is equal to u to the 6th, and my inner function is x cubed plus x minus 1. So my g prime is going to be df, or dg, du times du dx, which is going to give me 6u to the 5th times the derivative of x cubed plus x minus 1 is 3x squared plus 1. So finally, back substituting all of that out, my u is x cubed plus x minus 1. So I get 6 times 3x squared plus 1 times u to the 5th, which is x cubed plus x minus 1, all raised to the 5th power. So now I've popped in and out of my chain rule twice to find f prime and g prime so that I could go back to using my product rule. So my original product rule is y prime is equal to g f prime plus f g prime. So that's going to give me, well, g was x cubed plus x minus 1 to the 6th. F prime was 3 x minus 2 squared plus fg prime. F was x minus 2 cubed, and g prime is 6 times 3x squared plus 1 times x cubed plus x minus 1, all raised to the 5th. All right, so now cleaning this up at least just a little bit to put our coefficients in front, we get 3 times x minus 2 squared times x cubed plus x minus 1 to the 6th. Pulling my coefficient here out to the front, I have a 6 times x minus 2 cubed times 3x squared plus 1 times x cubed plus x minus 1 all to the 5th power. So, as with all of our other rules, we can mix the chain rule in. So inside of our product rule, we had to use the chain rule to calculate f prime and g prime, and then pop back out to the upper level and plug the f prime and the g prime with the f and g back into the product rule. So remember, we have to push in and then pop back out as needed. All right, example B is probably my favorite derivative in the history of the universe. And I have no idea why this derivative makes me so happy, but it does. So the first thing we're going to notice is it looks a little different than some of the ones that we've seen so far. So I have y equals e raised to the e, which is raised to the e, which is raised to the x. So we have e to the e to the e to the x. So this is actually a triple composition. So if we let y equal e to the u, we would then let u equal e to the v, and we would let v equal e to the x. Because if I back substitute all of these things back in, I would get my original function, right? So let's color code a couple of these for ease of use. All right. So then, the chain rule with more than one composition we differentiate through all intermediate variables. So our chain this time, instead of being a 2 chain, is going to be y prime is going to be equal to dy du, so y and u. Then the next thing that chains together is u and v. Then we do du dv. And then we chain our next one together, which is dv dx. And notice we're trying to find dy dx, or y prime. And if we were to look at it this way, the du's would cancel, and the dv's would cancel, and what would be left? Just dy and dx, which lets us know that we actually set up our chain rule correctly. So now we're going to plug in all of these things. Well, dy du, well, the derivative of y with respect to u, well, derivative of e to the u is just e to the u. The derivative of e to the v is going to be times e to the v, and the derivative of e to the x is going to be e to the x. Now we have to back substitute. Well, we were doing that in all the previous examples, but there was only one substitution. Now we've got it in layers. And we'll notice that u is a function of v, and v is a function of x. So we have to substitute out our u's first. So we're going to have y prime is equal to e to the u. Well, that's going to be e to the u, and u is e to the v times e to the v times e to the x. But now we need to substitute out our v's. And what was our v? Our v is e to the x. So we end up with e to the e to the e to the x times e to the e to the x times e to the x. So then finally, after back substituting out both u and v, we get e to the x times e to the e to the x times e to the e to the e to the x. So the derivative of e to the e to the e to the x is e to the x times e to the e to the x times e to the e to the e to the x. I don't know why that one makes me so happy. It's like this tower of e's. It's beautiful. That pattern holds, by the way. If you compose a fourth one in there, you would get e to the x, e to the e to the x, e to the e to the e to the x times e to the 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 x. What's that? So, kind of a fun little derivative. All right. We got time for one more. So once again, we're going to have a bit of a chain. So we have a cosine. Inside the cosine, we have an e. And inside of the e, I skipped one, didn't I? Let's do this one. So we have a secant that is being squared, and we have a sine theta. So our functions are going to look like this. We have y is equal to u squared. U is equal to secant v, and v is equal to the sine of theta. So using our 3-chain, our derivative is going to be y prime is equal to dy du times du dv times dv d theta. So dy du is going to be 2u times du dv. Well, the derivative of secant is secant v tangent v. And then the derivative of sine theta is going to be cosine theta. And now we have to start back substituting. So y prime is going to be 2 times u is secant v times another secant v. So secant v tangent v times cosine theta. So that's going to be 2 secant squared v tangent v cosine theta. And then we substitute out our v's, and our v's are sine theta. So we get 2 secant squared sine theta times the tangent of sine theta times cosine theta. And that is going to be our derivative.